Welcome back, guys. I have potentially one of the easiest AIME problems to date from the 2022 AIME 1. This is the 9th problem, 9 out of 15, so it should be about one of the harder questions, but let's read it. The question goes, Alina has 12 blocks, 2 of each are of red, blue, yellow, green, orange, and purple. Call an arrangement of blocks even if there is an even number of blocks between each pair of blocks of the same color. For example, this arrangement is even. Now, Elena arranges her blocks in a row in a random order. The probability that her arrangement is even is m over m, where m and n are relatively prime positive integers. Find m plus n. Okay. So in other words, this is a probability or counting question, which is asking us, well, can you find the probability that a random arrangement satisfies this given condition? And remember, the goal of this video is to really just give an overall insight into how we might go around discovering these two techniques to solve a problem. If you want more rigorous definitions, then you can always check out the AOPS user community submitted solutions. But this first method uses the parity property, which is evident here, and I'll attribute this to Aryan which is the first person I found out this method from. So for this problem, we will just take a look at the arrangement they're going to give us, right? So they give us R, red, blue, blue, yellow, green, green, yellow, red, orange, purple, purple, orange. And the first thing to do here is to think about, is to write out the positions of each of these blocks. So maybe because we might see a relationship between the numbers. So I'll call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so what do we notice about these numbers? Well, let's see. If we check for each color, let's record the positions of each of them. So red is at 1 and 8. Blue is at 2 and 3. Yellow is at 4 and 7. Green is at 5 and 6. And then orange and purple are at 9, 12, and 10, and 11. And so we see for each color given in the example, one of the positions is an even number and one of them is odd. But is this necessarily true for any even arrangement? Because this is only one example. So what is actually happening here? How do we define what it means to have an even number of blocks between two colors? Well, if we take a look at the position, it means subtracting one position from the other. So for example, for red, that would be 8 minus 1. But in order to count the number of blocks in between, we also need to add 1 back. So, we also need to subtract 1. So this would give us that there are 6 blocks in between the two reds, and that is indeed true. Okay. But so what if we had both of the positions of the red blocks? What if they were both odd? If they were both odd, let's say 7 and 1, we would have 5 blocks that are between the two red ones, which means that the arrangement wouldn't be even. And let's say that the positions were both even. Let's say our red blocks were at the 8th and 2nd position. Well, then we would have 5 blocks again in between the two colors, which means the arrangement is not odd. So what's actually happening here? We'll take a general definition. We'll suppose that an even number is really the same thing as 2m, where m is an integer, and we suppose that an odd number is 2n plus 1, where n is also an integer, right? What happens when we have two positions for our blocks for our red blocks, and one of them is even and one of them is odd, represented by these two numbers? How do we determine how many blocks are between them? Well, we subtract, just like we did before. We subtract the two numbers, and we add by one. We subtract by 1, which gives us a total of 2m minus 2n minus 2 blocks. And if you notice this is just equal to 2 times m minus n minus 1. Because m and n are integers, we can say that m minus n minus 1 is an integer, so the output is going to be an even number. It's going to be some even number. And we need even numbers, an even number of blocks between our two red blocks, in order for us to have an even arrangement. So yeah, indeed this is true. So now we can rephrase the problem into saying, well, how many, it seems like for each color, one of the blocks is going to be on an odd position, and for the other block, it's going to be on an even position. So really, we can separate the odd positions and the even positions. So considering the odd positions, we have 6 odd positions, and we have 6 blocks that we need to fill in those odd positions. So that's going to give us 6 factorial ways to fill in those colors. Now let's take a look at the odds. Now the odd colors, there's 6 even positions, and we have 6 colors. So once again, that's going to be 6 factorial ways to color it in. 6 factorial times 6 factorial, the total number of ways we can arrange blocks so that they are in an even arrangement. So this is the total number of ways. If we want the probability a random arrangement is even, we have to divide it by the total number of ways we can arrange the blocks. And how do we do that? Well, there's 12 blocks, so 12 factorial ways to arrange it. And then because we have matched pairs between the colors, we have 6 pairs of 2. We would divide that 6 factorial by 2 to the 6th to account for whenever we swap the 2 colors together. Okay, simplifying this down, our answer turns out to be 16 divided by 231. And so if we wanted to give the answer in the form of m plus n, then our answer would be 231 plus 16, which is 247. Now this is a really cool answer, because we're kind of skipping over a lot of the nuances which come that arise with this kind of problem. But let's move on to method 2. Method 2 I will attribute to a AOPS user by the name of I believe MC21S. And the general gist of the solution is, instead of looking at invariance, we're going to look at other ways we can determine whether an arrangement is even. So this time we're not counting. Let's say that we're given an arrangement of blocks, and we want to determine whether it's even. So I'm going to take the example again. So that's R B B R Y G G Y R O P P O. So we're going to ask ourselves how we can determine whether this sequence is even. Well, let's take a look at this. We can try a recursion on our blocks. because right now we have 12 blocks and 6 colors, but our problem would certainly be simplified if we could somehow convert this into a 10 block arrangement with 5 colors, and then maybe we can remove one more color and make it 8 blocks, and then make it 6 blocks, make it 4 blocks, and then eventually, when we're down to 2 blocks, there's really only one arrangement, and it has to be true. So the question is, what function will preserve evenness? So what do I mean by this? Well, for this, we have to do a little bit of creative thinking, and I'll give you the function. We take a look at the leftmost color, which is red. In this case, it's red. I will remove red. I just realized I labeled this wrong. We will remove red from the sequence in a very particular fashion. Once you remove red, notice that the red on the right side will split the sequence of blocks into 2 parts. We are going to remove red while flipping over the second half of the sequence. So this O would flip over there, this O would flip over there. And there's a very specific reason for that, which we'll talk about later. But essentially, it will preserve evenness. Why? Let's take an example. So now we'll go back to a parity argument. Remember, our parity argument is that, if we have 2 blocks, one of the positions has to be even and the other has to be odd. So if I look at the positions of each of the blocks I have right now, I'll label it again for us. How can I determine that this flipping will preserve the parity of each block? So for this, we'll take a little bit of a different example. Instead, I will replace in this case, this is a bad example because the part we're flipping is already symmetric, so it doesn't change anything. But maybe this last part isn't symmetric. Okay. So yeah, let's say we have a bunch of blocks, and they're gonna be A, B, C, D, E, F, and then we're gonna have red, just to be consistent a little bit between the examples. A, B, C, D, E, F, G, H, I, J. Okay? So what does this function actually do? Now, if we actually take this example, the first sequence will be preserved, so their parities will remain the same. We still have 2, 3, 4, 5, 6, 7. Their parities will remain the same, but the flipped over sequence will be J, I, H, and G. And so how is the parity changed from start to finish? The J started as a 12 and it ends as an 8. So it stayed even. The I started as 11 and it ends as a 9. The H starts as 10, it ends as 10. The G starts at 9 and ends at 11. So the parity is for each individual unique block. The parity remains the same. Parity is constant. This function has the invariant of the parity of the positions. So in other words, because we know an arrangement is even if for each color the 2 blocks are on one is even position and one is odd, this function preserves parity. And when we preserve parity, I know I spelled that wrong. When we preserve parity, we also preserve evenness. Okay. And there's one other nuance to this function, which I'll get to later. So in other words, this is saying if my initial if my initial sequence is even, then my output will also be even. My output sequence will also be even. The one nuance about this is that you will find a situation where you might find a situation where parity is not preserved. In this case, why does it work? It works because the sequence following the R is even. How do we know that? Well, simply, if we want this function to be even at all, we know that the number of blocks between the R's is even. And because we always, if the number of blocks between R is even, then the number of blocks out here has to be even as well. Because if it was not an even number, then everything would be completely different. Like, for example, suppose I have some sequence R, R, and then A, B, C, this time an odd number of items out here. Now, if I list my positions as 1, 2, 3, 4, and then remove my R's, then I'm left with C, B, A. Clearly, the parities have changed. B changes from 3 to 2, and it's not preserved. But because if my initial function is even, meaning the R's are an even number of blocks away, then my second half will also be an even number, and parity will be preserved. So against all odds, if the initial is even, the output sequence will also be even, and by the contrapositive, if the output is not even, then the input is not even. Okay, so how can we use this information to determine if a sequence is even? Well, we can suppose that if R and the other R are, if the entire sequence is even, what's the probability that R has an even number of blocks in between it? Because that is the first necessary condition. Well, in the first case, after R there are 11 blocks, and R can be placed at the beginning, right next to the other R, or it can be placed at the ends of the 12 block sequence, because there would be 10 blocks in between it. So out of 11 positions, there's only six positions for the second R, which would allow my function to would allow my sequence to be even, and at least allow my function to work. So 6 out of 11 times I will be able to apply the function one time, and we'll see if it's even. Now we have a reduced function, and what we're going to do is we're going to recurse. We're going to repeat the same thing. So this time, in my actual example, we'll take a look at B, and now B is going to be our new color that we're going to get rid of. And then we look at the second half that the second B produces. So this time, the two colors are right next to each other. We look at the second half, and we do the exact same thing as we did before. We'd flip over the entire second half of the sequence. And if B abides by the even rule, my flipping function, my removal and flipping function, will preserve evenness. And you know, if B does not abide by the even rule, then my entire function, by parity, my entire sequence cannot be even. So what's the chance that the two B's abide by evenness? Well, how many positions could B be in? It could be 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 positions. B can be at the beginning and the end. That gives us a total of 5 out of 9 positions that B enables parity. And now we just do the same thing. We do the same thing. So we're testing for each color. Every time we remove a color, what's the probability it's at a position, which allows us to keep checking for evenness. Otherwise, the sequence cannot be even. It cannot be even. We continue this for 4 colors. So we would check it for O next. So we have 4 sevenths. Then we check it for 3 colors. And we remove another color once more. We check it for 2 colors. And then we check it for 1 color. And merely, if you think about it, 1 color is just going to be like R and R. There's only one position for the correctness, and that's just 1 over 1. And once you multiply these probabilities together, the answer is indeed 16 over 231, which gives us a total of 247. 2 amazing methods to get the same answer, both using this parity property. The first one, albeit, is very simple, but this second example does show a pretty instructive invariance on parity. I'm going to show you a bogus method. It's bogus solution time, because even though this method is completely wrong, it does show, some good examples of, how we can improve on, our previous methods. And, it kind of reveals how strange this problem posed is, because, everyone's kind of complaining that this problem is very simple, but it can be very tricky if you interpret it the wrong way. So I'll bring up the example sequence again. And by the way, the bogus sequence is mine because I got it wrong. So the initial sequence, if I remember, R B B Y G G Y R O P P O. Now I sort of started off by noticing there's sort of a pattern which you can group the blocks together. You can kind of enclose the blocks. So for example, these 2 reds, enclose this entire region, and this entire region is composed of more subsets. And then we have these 2 O's and these 2 P's that have their own grouping. And so I kind of call this as a grouping. And I assumed this was the same kind of problem as a parentheses problem. If you're unfamiliar, there is a problem which asks you to find the number of ways you can arrange parentheses, open and close parentheses, such that the parentheses will correctly enclose a sequence. So I thought this was an analog to the colored blocks, that they are also enclosing, subsequences. And I assumed that these groupings can't intersect each other. So this would fall under Catalan numbers. So the use of Catalan numbers it's simply, for this example, if we have 6 groups of parentheses, so 6 pairs of parentheses, Catalan numbers give us the number of ways we can arrange those 6 pairs of parentheses, in this case 6 pairs of colors, into a sequence. And according to Catalan numbers, the formula is really rather simple. Whatever n number of colors we have, the number of arrangements will be 1 over n plus 1 times 2n choose n. And for 6 colors, this turns out to be 132, which is a far cry from the actual answer, which is, I believe, 720 arrangements, orderings of these colors, without taking into account color permutations. So obviously we're undercounting. What are we missing? Well, there's actually going to be a situation when these groupings intersect each other in a way that doesn't satisfy this Catalan problem. Can you think of a simple example that allows these groups to intersect? You can pause the video and try to find out. But the simplest example I will give you comes when you use 3 colors. The first thing to write down would be to write 2 R's and then wonder, is there a way, well, these 2 R's will group together like this. Is there a way I can write colors on both sides of the R so that their grouping will intersect, you know, the outside and inside of this region? And yeah, there is. If you write, let's see, yellow and green, clearly both yellow and green have an even number of things between them. However, they certainly intersect my groupings. So in this case, like something like this would be the equivalent of having parentheses that look like this. Actually, this is correct. This is a correct example, but the parentheses are not. They are intersecting each other in a way that doesn't exactly make sense. Okay, so in other words, my Catalan example doesn't work. There are many arrangements which can include intersecting groupings, and that's why we're getting a much lower number. And this especially scales up for 6 colors, as we can clearly tell. So this is no Catalan an analog. It's important to keep counterexamples in mind. They can be very instructive on how you go about things, and indexing and looking at parity and keeping in mind that even is such an important part of the problem, certainly the way to go. So what do you think? This is certainly one of the easiest problems of AIME, but I believe it's a very instructive counting one. All right, that's all. See you guys. 1, 2, 3, 4, 5, 6, 7, 8, 9,